That's okay. Don't worry about it, because it's only going to be on for a second. This same man tried to thwart the scientific evidence that was showing the Earth was standing still in space. Okay? He tried to thwart it. He saw it, didn't like it, and tried his best to get it out of our thinking. This man hated the Catholic Church. He was not a very good moral character. If you want to study his history.
It's in your book.
It's in my book, yeah. So if you want to know the dirty laundry of Albert Einstein, it's all there, scientifically and morally speaking, okay? And he tried to thwart the evidence that the Earth was standing still in space by developing his theory of special relativity. Okay? Let's see how he did that. In the 1800s, a half dozen experiments showed the Earth wasn't moving. In 1800s. This was like, the Industrial Revolution of science that was taking place in science at this time. All kinds of discoveries and experiments were being done, and it was just a boom of knowledge, flowering of scientific knowledge like we've never seen before. And among those were people who were studying the effects of light and cosmology and everything that has to do with that. And they started in the early 1800s, and the first guy was Dominique Arago, a French scientist who did experiments in 1815 and 1818, two of them, two different kinds of experiments that showed the Earth wasn't moving in space. Now, I could go into them, but my books do. All the information is there, yes?
Real quickly, he focused his telescope on one star, and when the Earth was closest to the star, and 182 days later, when the Earth is the other side of the sun in a heliocentric system, and therefore 186 million miles difference, he thought, well, I'm going to have to readjust my focus to keep a sharp look on the star, but he didn't have to adjust his focus. It was as sharp on one half a year later as sharp half a year later.
Yeah.
And this stunned the scientific community.
Mm-hmm.
This means the Earth isn't moving.
Yeah. Thank you. He's my best student, by the way. There was another guy, George Bedell Airy, a astronomer royal from England. That's the highest you can go. Did a very interesting experiment in 1871. I could go into that, give you the details of that. It's even more fantastic than Arago's experiment. And he showed
one telescope filled with air and one with water.
That's right.
With water, they expected the beam of light would be reflected, refracted to the side, but it wasn't. And they were shocked. That meant the Earth was standing still.
Yeah, because if the Earth was moving, the light beam would have been bent because of the movement of the light beam, and it would hit the wall of the telescope. It didn't hit the wall of the telescope, so obviously the Earth isn't moving. And this experiment still hasn't been answered until even today. So there you go. Another one. Then you had Albert Michelson coming along in 1881, worked by himself at this time, did an even more sophisticated experiment called an interferometer experiment that measures the differences in the wavelength of light. And in that experiment, it was thought that if you shot the light beam in the direction that the Earth is supposedly going around the sun, that somehow this light beam would be impeded in its speed because it has to go through space, or what they then called ether. And if that was the case, then we should be able to measure how fast that light beam and its speed were impeded by this ether. If it's 30 kilometers per second that the Earth is going around, well, we can tell you exactly what the wavelength is going to be impeded in that light beam. They can calculate it out, okay? And they got a result that they didn't like. And that was that the Earth wasn't moving because there was no impeding of the speed of light. If there was, it was just a little bit. And so,
1/6.
less than 1/6, yeah. And so they did the experiment again 6 years later, and this time he got a partner, Edward Morley, to work with him. And Alexander Graham Bell had funded it, and it was proved by physicists all over the world. And they wanted to make sure they got it right this time, because if they made a mistake last time and found out that the Earth wasn't moving, they wanted to make sure that this thing was precise and no mistakes would be made. They put it in a mercury bath, so it would take care of all the vibrations, because in an experiment like this, when you're dealing with the wavelength of light, a man walking 100 yards away on a sidewalk can cause enough vibration to throw this thing out of kilter, okay? So you have to make sure it's solid, and they did. Lo and behold, they found that the Earth still wasn't moving. No matter how precise they made, the more precise they made the experiment, the more they found out that they were wrong in assuming the Earth was moving, okay? So this was some big happenings here. And then Michelson did the experiment again by himself in 1897, and guess what? Same results, okay? Earth wasn't moving. So everybody's scratching their head trying to figure out what to do. Here's Neil deGrasse Tyson talking about this experiment. Up the volume. Let me see. Is that the volume right there?
Here comes Liz.
Far right.
The volume. Yeah, the speakers are not picking it up. Yeah, the speakers aren't picking it up. That's the problem. What's that?
Put the microphone in front of the speaker.
I don't hear anything from the speakers. I only hear it from here. Let's play it again. Play it again, Sam. Is anything coming out of the speaker? No?
Oh, you know what? Because it's connected HDMI.
All right, I'll play this again, and you put the microphone on where it's coming out.
Yeah.
Experimental advancement technology that transforms science.
Let's do it again.
Not only physics, but science.
Okay, here we go.
One of the Brashear Company's major contributions to science was the construction of the extremely precise optical components for the Michelson-Morley experiment of the late 1800s.
There are only a handful of experiments in physics that completely transformed physics. And many people's top of the list would have to be the Michelson-Morley experiment. It was an experimental advancement technology that transformed science. Not only physics, but science.
Okay, there you have it. Right from the man. Did you hear what he said? You did hear what he said, right?
Yes. Could you put it in presentation mode so we can see this?
Well, it's not going to make any difference at this point because these are all, I don't think you can, yeah, all it's going to do is switch the screens. Yeah, so can you put it back where it was?
Oh, you don't want it that way?
No.
It's hard for them to see
Yeah.
the screen there.
Yeah, but it's not so much seeing it, it's what he said is important. And what he said was that this experiment was probably the most important experiment in all of physics up to today. Why? Well, because it showed that the Earth wasn't moving, and we can't have that. So we have to figure out a way to get out from under this burden. Because if we are wrong and we've been wrong since Copernicus for 500 years, then we're going to end up kissing the feet of the Pope, you see. And we've already shown that Catholicism is way behind the times when it comes to science, and we are just so far superior to them. And something has to be done to get out from under this conundrum. And so we needed a genius to come along and figure things out for us. What went wrong? Okay. So here we go. In the book, Einstein, The Life and Times, published in 1971 and republished in 1984, talking about Einstein's life and what everyone was thinking after this Michelson-Morley experiment was done in 1887. And here are the author's words summing up the problem. He says, "The problem which now faced science was considerable, for there seemed to be only three alternatives. The first was that the Earth was standing still, which meant scuttling the whole Copernican theory and was unthinkable." There you have it. Unthinkable.
Einstein said that?
No, he's saying that,
That's his quote.
no, that's not, that's the author's quote. His name is Ronald Clark. So basically what Clark is doing is getting the consensus of all the physicists in the world at that time and what was the possible solution. Well, one of them was to say the Earth was standing still in space. You could easily answer the Michelson-Morley experiment, but no one wanted to consider that possibility. There had to be another possibility. Someone had to think of another possibility. Okay? Yes, ma'am.
We couldn't see that. Could you explain what the Michael-Morley experiment was?
Yeah, I did briefly, which was they shot a light beam into the direction they believed the Earth was moving around the sun.
They shot it east. And they also shot a light beam north and south, where we don't think there's any movement.
Actually, they shot it west, east to west, and then they had another beam that they shot north to south. And the theory was that the beam shot from north to south should not be affected at all, because it's not going into the ether. It's not going into space. Because if the Earth is going around the sun, that means the Earth is going at 30 kilometers per second through this whatever it is around the sun. And so if it is, and you shoot a light beam toward that direction, then that light beam should be slowed down to some extent. Okay? Because it's going through this ether that's in space.
And if it's slowed down, there's going to be a fringe shift at the camera measuring, and there wasn't. Both light beams had the same speed.
She doesn't know what a fringe shift is, so what we would have to say to explain it is when they compared the speed of the one beam that's going with the Earth around the sun, that should be slower than the one that's going north and south.
It wasn't.
And it wasn't. Actually, it was a little bit, but not by much. Not hardly enough to account for an Earth going around the sun at 30 kilometers per second. It was more like 5 kilometers per second. That's all they saw, okay? But if the Earth was going around the sun at 5 kilometers per second, okay, it would take 60 years for the Earth to go around the sun, okay? So can't count that in there. Yes, sir?
So it brings exactly to that point, since the result was not null, but it was small, why in the book you interpret that as the Earth not moving, but just ether drift as opposed to the Earth moving forward?
Well, because it's either all or nothing in this case. You either have 30 kilometers per second or you don't. If you have anything less than that, then you can't say the Earth is moving around the sun. Now, if you had 29 kilometers per second or 28, okay, you could say within the margin of error, you're correct. Earth is going around the sun. But this is like 1/10 of what they wanted to get. They got 1/10 of what they wanted to get. So,
And in subsequent tests, only 1/20th.
yeah, and they just repeated the same experiment over and over and over again for 50 years. From 1881 to 1930, the last guy to do it, his name was Joos, Joos. And every single time, they never found the speed they needed for the Earth going around the sun. So this was probably the most important experiment, repeated more than any other experiment man has ever done. And the results never changed. So that says something. Yes, ma'am.
At this point,
Ether, okay. Okay, so let me ask you this. What is between the Earth and the sun? Or what's between Earth and the moon? Space. But what is space? Some people will be tempted to say it's nothing. Space is nothing. Well, if space were nothing, by definition, nothing doesn't exist because it's nothing. Okay? So you can't say space is nothing. What's the opposite? Space is something. What is this? What is this something? Well, that's to be discovered. But it's not a nothing. It's a something. So let's call that something ether. Now here's the irony of the whole thing. Einstein, in order to keep the speed of light constant, took away the ether. If you take away the ether, then there's nothing to decrease or increase the speed of light. So it stays constant. Okay? That's in his special theory. In his general theory, guess what?
It bends, it has to bend the light from,
Well,
the bending effect.
yeah, but he took the ether back.
Yeah.
He took the ether back. Okay? So this is why I'm covering two sides of Einstein. You got the one side that we can use for our side, but then you got the other side that's the Dr. Jekyll, or a Mr. Hyde rather, of this whole business.
Are you going to talk about the Eddington experiment where they measured the bending of light during a solar eclipse?
I wish I could. Yeah, I wish I could. I don't have time for that. Yeah, some other time. Yes, ma'am.
I was just trying to understand, if that ether is, we don't know what it is, does that mean that if a spaceship was traveling, if it was traveling, that there would be nothing to hinder the speed of light? Can you measure how fast something could go or not go out there?
If you had ether or not ether?
Well, we don't know what's out in space. We just know it's something.
It's something. So let's just say,
How is there anything then that would hinder us? You know, I mean, I've read science fiction stories and all this stuff, and they'll say, well, such and such went the speed of light, or they went faster than the speed. Is that a possibility? Is there anything that would hinder a spaceship from going any particular speed out there?
well, let's agree to this. There can't be nothing out there. There must be a something. We're going to label that ether. You can call it smeether if you want. I don't care. But we're going to label it something.
But we don't know how it would respond.
We do. We do. I'll get to that. Okay? So let me build a case first, and then we'll get to specific questions like that. Okay? All right, so here's a contemporary of Einstein. His name is Hendrik Lorentz. And this guy was probably the premier physicist in Europe at the time. And he couldn't figure it out. He figured, well, I'll tell you what, best that I can do is we'll say that the arm that shot out the light beam in Michelson's experiment somehow got shortened, and so the light beam didn't have to travel as far, and that's what's making up the difference. You know, I mean, I feel sorry for these guys because they really were grasping at straws. They just didn't know. But you know, this very theory of Lorentz's survives today. It's called the Lorentz contraction theory. That if an object moves, it contracts by a certain measure if it moves. So they haven't relinquished this today. But when they heard it, Lorentz said, everybody's laughing at me. And his partner over there in Ireland, Fitzgerald, he said, yeah, they're laughing at me too for suggesting this, okay? And, but he kept the ether. He kept the ether and he said, okay, it's the ether that's shortening this tube that the light's coming out of. So when the Earth moves against the ether shortening the tube so the light doesn't have to travel as far. Okay? That's called the Lorentz contraction theory. And that stood in place until Einstein came along in 1905. Because Lorentz had proposed this in 1892. Okay? All right. And Lorentz, after he's done all his work, he comes up with this statement at the end of one of his papers and says, briefly, everything occurs as if the Earth were at rest. Every time he tries to do an experiment, this one was dealing with stellar aberration, which is another topic I can't get into today. But that was used as proof of heliocentrism, stellar aberration. And Lorentz starts to examine stellar aberration and he finds out, you know what? Let's be honest, everything occurs as if the Earth were at rest. And all we're doing is playing games, trying to make it look different. Okay?
So he admitted then that was this his final contribution, or after that?
No. He still believed the Earth went around the sun. He's just telling you that it looks like everything occurs as if the Earth were at rest. That's all. That's all he's going to admit. And here's the letter that he wrote to Lord Raleigh. This is the actual letter. I went to look this up in the microfiche. There was a copy of it. And this square right here is this square right here is quoted here. And so I'll read that for you. Quote, I could account for all the observed phenomena were it not for the inferential experiment of Mr. Michelson. I am totally at a loss how to solve the contradiction. Can there be some point in the theory of Mr. Michelson's experiment which has yet been overseen? Okay? He's looking for a way out. But how many times did they do Michelson's experiment? 50 times from 1881 to 1930 without deviation. Oh, there's a little bit of deviation, but nothing to write home about, okay? But you just chalk that up to margins of error in experiments. They're not all going to be perfect, that's for sure, okay? So here he is scratching his head. He doesn't know what to do. Okay, then comes along Einstein. In his special relativity theory, Einstein had an ingenious solution. Instead of making the Earth fixed and absolute, Einstein found that if he made the speed of light fixed and absolute, then the Earth had to move. That's pretty clever. He did so by taking away the ether. And now there was nothing to decrease or increase the speed of light. Okay, so Einstein basically had two choices. Keep the physics as we have known it, that ether exists, and that light is impeded by it to varying degrees, or invent a whole new physics so that we can keep the Earth moving. Because, come on, gents, You know what keeping the Earth moving means to all of us, don't you? Yes, that means we won't have to kiss the feet of the Pope. The Galileo was right, and Newton was right, and all the scientists that came after in the Enlightenment, they're all right too. Okay, that's what's at stake here. So if it's just a matter of picking which one is going to stay fixed, speed of light or the Earth, what do you think he's going to choose? Light. Yeah. All right, so there you have it. And here he is smoking his pipe. And there's his equation that he used. Guess what he used? He used Lorentz's contraction equation. The guy that just said that the reason the light beam didn't go the speed we expected because the tube it was coming out of was shortened by the fact that it was moving against the ether. Well, Einstein didn't like that explanation, but he liked the equation. So he used Lorentz's equation. And that's the equation that you saw him writing down there. It's 1 minus 1 times the speed of the object squared over the speed of light squared, and you take the square root of that, and that's your result. And it's always less than 1. It's always less than 1, no matter what v squared or c squared is. So that's it. I mean, that's not much more you can say about that. That's what he did.
You needed to squeeze gummy bears more often and find out they get fat when they get short.
Oh, yeah, they did that too. All kinds of people were saying, well, if you do that, then this happens. You do that, then this happens. They were going back and forth on this, but everybody liked the end result. The end result was we didn't have to kiss the feet of the Pope, and the Earth was moving. Who cares how you get there? The ends justifies the means, basically, is what they're working on. Okay, but 10 years later, as we have already delved into, in general relativity, 1915, he had to take back the ether and was forced to make the speed of light variable. Okay? And here's a quote from him. According to the general theory of relativity, space without ether is unthinkable. So, okay, well, what does that say then for your special relativity theory that was used to answer the Michelson-Morley experiment? That means you don't have one now? Well, they don't talk about that. Okay, nobody likes to talk about that, except me. When I bring it up, and, they just shoot me down. They get everybody together, they just shoot me down. He's an idiot, he doesn't know what he's talking about. But I'm the only one who brings up that contradiction. Okay? Everybody else is happy to live with it. And he had to admit that the Earth could be in the center of the universe and act as its center of mass and therefore be fixed in that place. That's what general relativity requires. And all the inertial forces that Newton said were fictitious were actually real forces that controlled all the celestial bodies so that they could remain in their positions. Okay, which is what I had said before, earlier, last session. Okay, so here I made a little joke up. Oh my God, I must be in a time warp. The ether is now my best friend forever. Even though I took the ether away in 1905 to answer the Michelson experiment so that I could claim the Earth was moving around the sun. Okay. All right, how does the geocentric system work? Somebody earlier was asking about the seasons. Well, here's a geocentric model of the seasons. Now, the sun we made small because that's what it looks like in the sky from the Earth, okay? And here it is traveling around. It's going around the equator now. And so that would be March or September on our calendar year, March 21st or September 21st. Now it's going up, and it's going to be at a 23.5 degree angle, and it's at the Tropic of Cancer at its maximum height, and that's June 21st in our seasons. That's actually 23.5. Tropic of Cancer is a little lower than the 23.5 degree mark. And now it's down below the Tropic of Capricorn at 23.5 degrees, and that's our December 21st, wintertime, the start of wintertime. Okay? So how does it do that? Well, the whole universe basically is going to go up and down. It's going to go up by 47 degrees and down by 47 degrees. Just as it rotates, okay, it's also has a vertical movement. The rotation is a horizontal movement. The vertical is the movement that controls the seasons, and that's between 47 degrees. Okay, so up 47, down 47, up 47, down, and that's how we get our seasons. Now you might ask, how does it do that? Well, remember we talked about the center of mass. Okay, the universe shares a center of mass with the Earth, but the universe has a different axis that it rotates on than the North Celestial Pole. Okay, we call it the universal axis. And that's tilted 23.5 degrees. And when you have that, you are not going to get a straight line motion for the sun or anything. You're going to get a wobble, or what they call a precession. Have you ever spun a gyroscope, a toy gyroscope? And when you spin it and then you hit it, what happens? The gyroscope still spins, but it starts to wobble. Okay, and in technical terms, that's called a precession. And so that's what the universe is doing. It's precessing. And as it precesses, it's going to precess horizontally and vertically. And that's how we get that 47 degree change every 6 months. Okay? Okay, and what is the universe going to do when it is moving around? Here we go. Anybody know what that is? That's a hurricane. Here's another hurricane. Notice anything different about them? Different rotation. Different rotation. Okay, so the one in the north is spinning counterclockwise. The one in the south is spinning clockwise. Let's take another look. Okay, that's in the north. That's in the south. Why is that? In the geocentric system, we explain this by saying that it's the Coriolis force. Remember I told you it was a turning force, okay? An inward turning force. That's why the Foucault pendulum can be turned by the Coriolis force, okay? Same with hurricanes. But since the Earth is in the center of the universe, guess what? It shares an equatorial plane with the universe, so that anything that occurs below that equatorial plane is going to be affected differently by the Coriolis force than things that are above that equatorial plane. So that things that are in the north are going to spin in the exact opposite direction of things in the south. Okay? And at the equator, there is no Coriolis force, and that's why we see no hurricanes at the equator. Okay? So remember I told you that the rotating universe creates the inertial forces, the centrifugal, the Coriolis, and the Euler. And the Coriolis, they're all involved here, but the Coriolis is the strongest one. Remember I said it has a magnitude of 2 compared to the centrifugal force, so that's what you're going to see most of all. All right, that's what's moving this hurricane, because the Earth is fixed, so what else could be moving the hurricane? There has to be some other force. It's coming from the rotating universe, you see, okay? And that rotation of the universe is split in two between southern hemisphere and northern hemisphere. Yes, sir?
So what is the heliocentric explanation for this phenomenon?
Heliocentric is just a geometric explanation. Remember, the Coriolis is not a force for them. It's just a change of direction. So as the Earth is spinning underneath, the water's not traveling with it. So it's going to form a vortex just by the fact that the Earth is moving underneath of it. There's no force involved, just a matter of direction. That's all it is. Okay? And then they'd get the opposite in the southern hemisphere because now you're below the equator. Make sense? All right.
So when the north goes in one direction, the south goes in the other direction. At the equator, since there's no Coriolis force, how does water flow down? But I mean, would this be the same with, you know how water going down the drain goes in one direction in the north and the other direction in the south?
Yep, same thing.
So at the equator, what would happen?
There is no force.
Okay, so it would go straight down. And
It would go straight down, or there might be some other effect, like air pressure, friction, you don't have the thing level. You know, there's all kinds of factors that go into which direction that water is going to go. Even in the northern or southern hemisphere, sometimes you get water in the southern hemisphere going in a counterclockwise direction. Well, that's because the mechanism wasn't set up right. Okay, but most of the time, 99% of the time, it's going to go in the clockwise direction.
in general, if you have the same flow in the north, south, and the equator, they would follow the same flow direction. But at the equator, the tendency that if it has a spin, it would be very small or no spin at all.
Yeah, or you might think you're at the equator, but you're a little above or below it. Yeah, but theoretically, yeah, it's going to go down straight. It's not going to have any turn. Okay? That's why the Foucault pendulum doesn't turn at the equator. And the Foucault pendulum, the direction that it turns in the north is going to be the opposite of what it does in the south. Okay? Same difference. All right, so here you have, here's the Earth, and here is a hurricane. Can you see my pointer? It's not that great. So here's the Earth. Here's a hurricane going counterclockwise in the north, and here a hurricane going clockwise in the south. And you have what we would call here the celestial equator. That is, the Earth is right smack in the center of the universe. And if that's the case, then you're going to get these two opposite reactions to this water. Okay? All right. Okay, in case you haven't seen a Foucault pendulum, let me show you one. This is at the Philadelphia Ben Franklin Institute. Now watch, you come back the second time. See it? Knock down that peg. That means it moved. All right. And then I talked about this before. Let's look at it again. This is the Earth spinning in a fixed universe. Now, we have the universe spinning around a fixed Earth. And you see the same effect, the bulge of the Earth. Okay? Now this tells you something, basically, that you can see why there's basically no difference. Because you're just holding one still and making the other go around it, and then you're holding that one still and making the other go around inside of it. That's all you're doing. Okay? And that's what I meant earlier about a coordinate transformation. It's very easy to understand. And they're both going to give the same result. Again, thought I... Makes sense, everybody? Clear as mud, right? All right, now, everybody asks questions about the geosynchronous satellites. If you've never heard that before, you should prepare yourself if you ever want to defend, geocentric cosmology. Now, what is a geocentric satellite? Geocentric satellite is a satellite issued into space that stays over one spot of the Earth all the time. And these are usually weather satellites. You ever see those maps that they have on the news shows where they're giving the weather and they show how the clouds are moving and all this stuff? Well, they get most of those pictures from those weather satellites that are over one spot of the Earth. They never move. So they can continue to take the same picture 24 hours a day, okay? And they can see the differences that happen in that one spot for 24 hours. Those satellites are about 22,000 miles above the Earth, above the equator, okay? And in order for that satellite to stay one spot over the Earth, what does that satellite have to do in the heliocentric system? Yeah, it's got to travel with the Earth. Now, at the equator, the Earth is traveling about 1,040 miles per hour, okay? You know what, let me go back because I have a... Okay, so there you have it. There is the Earth moving around at 1,000 miles, about 1,000 miles per hour at the equator. And that satellite out there, the white thing on that red disk, is 22,000 miles above. And so that satellite has to travel a whopping 7,000 miles per hour in order to stay up with the Earth spin. Okay? So that means they have to give it a thrust of 7,000 miles per hour. And what they can do is they can have this satellite be shot into space at a different declination or a different speed or a combination of the two. And what that will do is create an incline in the trajectory of the satellite. And you'll see this figure 8 that it makes. Can you see that from back there? Figure 8, red figure 8. Anyway, that's caused, if you held a pencil on the Earth while this satellite was moving, it would make a figure 8. And they can make these into figure 9s or anything they want. Like if they want the satellite to stay up here and give most of its power or most of its time up here because they want to have Sirius XM, they want to spend most of their time in one particular area of the world. And so you can make this satellite stay up here about 75% of the time and down here about 25% of the time, depending on how you shoot it into space and how fast you make it go. Okay? But that's not of our concern right now. What our concern is, we know how the heliocentric explains this. How does the geocentric explain it? Oh, I wish this was easier. Okay, so in the heliocentric version, here's a satellite. It's going 7,000 miles per hour in this direction. Okay. The satellite's 22,000 miles high. And inertia is making this satellite continue at 7,000 miles per hour, and it's going to try to go in a straight line. But the gravity of the Earth is going to pull it, and thus the satellite is going to go around in a curved direction. Okay, everybody with me? Okay. Now, this is when you guys start to get tired, and I see some faces out there that are shutting their eyes. So I catch you, I'm going to put this laser beam right in your eye. All right, so here's the geocentric version, okay? We got almost the same thing, except the Earth isn't moving. It's at 0.0 miles per hour, okay? Now, the satellite needs to stay in one location above one spot of the Earth. There it is. It's got to stay above that spot. But if the satellite stood above that spot, all by itself, what would happen? Come on, one of you geniuses out there. Come on, tell me. Well, wait. Don't go there. No, just all by itself. Don't worry about the universe yet. It is, no? What's this thing called? Right here. Gravity's going to pull it in. Okay? So, what happens here is, if the Earth isn't moving, what's moving? Mr. Mudd? What's moving? The universe is moving. Okay? East to west. How fast is it moving at 22,000 miles high? 7,000 miles per hour. What is in that universe? Not nothing. Yeah, we got something in there, right? We haven't discovered what that is yet, but it's something. And what else do we have? Remember those forces I talked about? Coriolis, the centrifugal, and the Euler. They're all out there. They permeate the universe. Okay? So they have a force that has to be reckoned with. Okay? So that's what that satellite's fighting against. So when it's moving 7,000 miles per hour, it's moving to 7,000 miles per hour against the universe that's moving 7,000 miles per hour in the opposite direction. And if you have 7,000 minus 7,000, what do you got? 0. That's why it can stay 1 point above the Earth. Okay? You got two forces fighting each other. The result is 0.
Does that use up a lot of energy to keep that satellite in the same space?
No, because the satellite has its own inertia. Okay? It has 7,000 miles per hour inertia against a 7,000 mile per hour universe that's rotating against it. You know, that's what inertia is. You know, nobody knows what makes that thing keep on going, but it keeps on going. It does, okay? So,
wouldn't the ether eventually slow it down? Is it going against the ether?
no. That's what's great about the ether. So far, it's not frictionable. Yeah. So, and that's good.
It transmits light and radio waves.
Transmits light and radio. So it does wonderful things for us, okay? And because light goes so fast, there will be an effect from the ether on that speed because light does go so fast. But material objects generally don't go anywhere near the speed of light, at least in our terrestrial environment, so we're not going to see much of a difference in the ether. And that's why we say it's virtually frictionless. Okay? All right, so basically if you want to round it out, and I'm a little over time here, this is your universe with the Earth in the center. And here you see your forces. The red is the centrifugal. The green is the Coriolis, and the orange is a centripetal force. Now that actually should be closer to the red, should be inside more. But these are those forces. Remember the Coriolis is how many times stronger than the centrifugal? Twice. So it's going to win the battle. And so it's going to keep all these objects right in that position as the universe goes around it. Okay? So basically you have your nuts and bolts of the geocentric system. And I think we're going to stop there. And then we got one more session coming up. Oh, remember I told you about Newton? This is the guy that I was reading his book one day on an airplane, Stephen Weinberg. He is a world-renowned physicist, Nobel laureate. And he has this paragraph in his book that I was shocked when I read it. And he says, if we were to adopt a frame of reference like Tycho's in which the Earth is at rest, then the distant galaxies would seem to be executing circular turns once a year, and in general relativity, this enormous motion would create forces akin to gravitation, which would act on the sun and planets and give them the motions of the Tychonic theory. That's everything I said to you in the last 3 hours in that paragraph. Coming from a world-renowned physicist, Nobel laureate. He says, and then he refers to Newton. He says, Newton seems to have had a hint of this. In an unpublished Proposition 43 that did not make it into the Principia, Newton acknowledges that Tycho's theory could be true if some other force besides ordinary gravitation acted on the sun and planets. And I already read that to you, remember? Let's read it again.
Hey, Bob, could you turn your pointer away?
Oh, I'm sorry. I was trying to catch that guy asleep back there. All right, so here is Newton's last page of the Principia. And I read you the paragraphs before. He said we can make room for the Tychonic system if we find that other force. Okay. Did we find that other force?
Yep.
We sure did, didn't we? We've been spending all afternoon on it. And that's, if you have a rotating universe, you have the force. It just comes in 3 parts. Centrifugal, Coriolis, Euler. Okay? And even Mr. Weinberg agreed that if you have that, it controls all the positions of the planets and the stars and the sun. I mean, what more could you ask for? It's all right there. Isaac Newton's grave is at Westminster Abbey. What do you think Newton is doing in there right now? Turning over, yes, turning over. Okay, all right, so that's it for this session, and we'll come back for the next session in a few minutes. Thank you.